everybody, here is my Lab 4. The objective for Lab 4 was that we had to create a model to predict the motion of a spring. We used Newton's second law to predict the net force, velocity, and position. We also needed to use the energy principle to look at the changes in kinetic, gravitational potential, and spring potential energies. The main result was that our computational model was able to predict the actual position fairly accurately, and that the energy principle was satisfied. Using Tracker, we obtained position data for the lab that we would use later on in our code. The calibration stick was set to be 0.7 meters from the fixed point to the end of the spring when it was hanging straight down. The origin was at the fixed attachment point and the mass was hanging in the negative y direction. The point of mass was the middle of our mass. From there we tracked the position of the oscillations as the mass swung. I pulled the x and y position data and recorded it in a CSV file for later use in our computational model simulation. I then put the time and the y position in an Excel spreadsheet to find the time step. To find the time step, I took the average time for 3 oscillations in the negative y direction that have about the same peak. The 3 oscillations that I chose are within the magenta box. From there I took the time of the last peak minus the time of the first peak and divided it by 3 to get my t to be 1.519 seconds. After getting the time step, I was able to calculate the spring stiffness. Here we used 4 pi squared times mass over time squared. After working the equation, it came out to be 6.878 newtons per meters. From there, we were able to find our relaxed length of our spring. This is done by setting the magnitude of the gravity force equal to the magnitude of the spring force. By rearranging the equation, we are able to see that the relaxed length of the spring is equal to 0.127 meters. We then turned to our code to input these values and other initial conditions into the code. The mass of our system is 0.402 kilograms. Our initial position of the system is at negative 0.112, negative 0.644, 0 meters, and our initial velocity is 0. The next section of code shows where we read in the position file from our tracker data so that it could be analyzed. The next section is some more initialization data. G is equal to 9.8. The spring stiffness and relaxed length that we found earlier is plugged in here, as well as the L, which is the length of the spring. L hat is the direction of the spring, and S, which is the stretch or compression of the spring. We then are able to use Newton's second law to add up all the forces that are acting on the system so that net force equals force of gravity plus the force of the spring. Once we have net force, we are able to determine the final velocity by taking the initial velocity and adding the net force divided by mass multiplied by change in time. Then we can update our position by taking our initial position and adding final velocity times change in time. This is the part of the code that shows where Newton's second law is taking place. We next turn to the energy equations that are needed. On the left, you can see the equations for kinetic energy, gravitational potential energy, and spring potential energy. Shown on the right is the part of the code that calculates each individual initial energy. This is where Newton's second law was helpful in finding the velocity and position. We then turn to our energy principle, where the total change in the system's energy is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. The next part of the code shows the updating that is happening to the energies. Now I will run the simulation. The black arrow is a gravitational force, and the blue arrow is a spring force. The red ball is the position data from the CSV file that we found using Tracker. In the graph, the green line is the change in gravitational potential energy, the red is the change in spring potential energy, the blue is the change in kinetic energy, and the yellow line is the total energy, which is equal to 0. As you see, the gravitational potential and spring potential are always opposite of each other, and the kinetic energies always cancel each other out. Since the red dot does not match it entirely, there is always room for human error while trying to track the system. We then look at the actual position versus the predicted position of the mass. The blue line shows the predicted position, and the red line shows the actual position. Just like I had said previously, there seems to have been some human error while marking the position of the mass while using Tracker. Overall, I would say that the model predicts the actual position of the mass quite accurately. For the first what does it mean question, it asks if the energy principle was satisfied. The answer to this is yes. The reason that it is satisfied is due to the fact that delta E has to equal delta K plus delta U gravity plus delta U spring. And here we are able to see that on the graph the line is equal to 0, which it should be. For the second question, for what does it mean, we had to look at the x and y positions within Tracker to find the time steps. As you can see, there's a difference of 0.101 seconds. This is due to the fact that the mass is moving back and forth in the x direction, meaning that there is more that is affecting it rather than in the y direction. This is why in the x direction there's a little bit longer of an oscillation period. Thank you.